All right, so I am going to cover the crustal component of the W array phase 2 models. So as you have seen this from Ruth, W array is really about cross-scale modeling of data collecting and modeling of the whole WRA's lithosphere. So the way we do this is, as you just have seen from Reza and Robert, they're covering the uppermost of the crust. And now I'm doing the whole crust and then pushing this slightly below the mohole. So I'm going to use conventional seismic, passive source seismic methods to get the crustal models. Here is my stations. So in addition to phase 1 and phase 2 WA stations, I also put the previous passive source temporary deployments like here, and inside probably some gray dots. These are from the ANU previous field campaigns. So I also have these 3 lines as you have seen this morning or on the wall there. These will be the model comparison with the active source lines. The technique are very conventional. Conventional, I mean, like this one, so-called receiver functions, this is probably like over 50 years old. The idea is very simple. When you have a P wave coming from below, say this is the mohole, the P wave will go through the mohole and then arrive the station here. That's one station. So that's what you see here, the so-called direct P wave at the 0 time. Or it's shifted, but anyway. And then some of the P waves energy will be converted to S wave. So that will be the red line, dashed red line here. So remember, black line is P wave, red dashed line is the S wave. And then this is the P to P mohole converted wave. So that's these signals. And then some of the energy will be like trapped in the crust, and they go multiple times up and down, and we call this the crustal reverberations. So basically, these have the information of the crustal P and S wave velocity, and also the mohole depth or crustal thickness. Below here, this is just a synthetic, like how would you see a receiver function? So they will be like this on 3 different components. And this is the real data, one of the WRA stations, like different frequencies. We all see the direct P wave and then the mohole signal here. And then these 2 are the multiples. So different frequencies just to show this is a very robust feature, and then this station is very good. And then we can use, for a single station, we can collect a lot of these so-called P-wave stations, and they come from different distance, or we can call them slowness, we can sort them and plot it, say that this is the mohole time and the multiple time. Remember, I was talking about the receiver functions has the information of P and S velocity and the mohole depths. And by combining this, we can just do a simple 2D search. And then, so along the mohole depth or crustal thickness, and this is so-called velocity ratio. And then for each point, we can actually predict the arrival times, and then we can sum up the receiver function signal. And then eventually, this is where the real mohole is. So this is just a very simple 2D approach, and then we can just stack to have average crustal thickness and the velocity ratio. Velocity ratio here is just used as the bulk crustal like composition. So this is a single station approach. And this is a map view of all phase 1 stations. So along these 2 profiles, like along the longitude, along the latitude, we can actually see each station actually has multiple events coming from all directions. And then by projecting the energy towards the source, we can actually form this so-called common common conversion point stacking method to get continuous information of the crust. So this is a single station H kappa, and this is multiple station CCP, common conversion point stacking. Another technique is the so-called noise tomography. So the idea here is for a station like Micathera here, we can actually form this so-called cross correlation. And then we can actually see, so this is sorted by station pairs for Micathera, say from its nearby stations like this, and then going all the way towards the very last one. So we can actually see this coherent signal. This is actually the surface wave between the Micathera, between each station pair. And then this is another example for this station, NWAL down south. Again, we see very clear surface waves. And then by using this, we can actually form different paths. And then this will form a natural tomography problem. And these two shows for phase, I think this is for phase 1, we can actually have very good signal. And then this is used to form the crustal 3D shear wave velocity model. I'm just going to show the models directly. These two are maps from the single station map. The left one is the crustal thickness, the H, and then the right-hand side one is the VPS ratio. And plotted on the maps are these dots. These are the gold deposits. I guess for phase 1 and phase 2, we see this pattern, I guess, earlier from the previous talks, that this structural trend, like a thick crust going like this, northeast, southwest, like this way. And then in the east, the eastern gold fields, we also have thick crust. And then I guess on the map here, we don't see much correlation, like whether the gold deposits favor thick crust or thin crust. I guess they favor both. And then on the right-hand side, the VPS ratio is approximate of crustal composition. The slow number here, like 1.7, 1.74, this is like in the blue area. These are small numbers, and we call them, this is the felsic crust. And then you can actually see most of the gold deposits, like the yellow dots, they tend to, favor the very small VPS ratios or the felsic crust. And then the next one is from the multi-pole station CCP stacking. This is similar to the crustal thickness, like the previous one here. But this one is like, because we have multiple ray paths, we can have seamless mohole, and this is it. This is the mohole depth, so it's continuous all the way. And then again, we see similar patterns like a thick crust in the east and thick crust down south. And then we have this sort of thin crust in this part. And it seems like some sort of crack going down in the center. On the right-hand side, this is the mohole amplitude from the CCP stack. So basically, the larger the number, like 10% here, means the crust gradient is really large, which is in previous talks when we talk about sharp mohole. So sharp mohole is really like focusing this part and only southern part of the eastern goldfields. I guess I've seen this. Basically, this is from Hugh's geology paper. The middle map here shows the age, like the younger part of the Yuan is here, the oldest is there, and then this is relatively young. And I guess just based on the crustal thickness, we don't see much correlation. Like you have young crust here, thick crust, but you also have relatively young crust, but this is very thin crust. So it's not directly correlated with the age, but this isotope northeast-southwest trend is probably reflecting in the crustal thickness as well. Like you see here down south, this is following this trend, and then the Q isotope zone is here. There's a little bit I guess we need more stations up north, but I guess there's still a trend like this. So these are the maps from the receiver functions, and for the noise crustal models, I'm just gonna show cross sections along these three active source lines. In the report, we have maybe like 10 or 11 different cross sections, which you can see more. But basically, the idea here is just to show, okay, where's my map? Okay, here's the map. So I'm gonna go back to show this one, southwest one line. For some reason, it was removed. But anyway, this is to the west, this is to the east. The top panel here shows the reserve function. So basically, this shows the velocity gradient, like you see the moho, the blue and the green. The line here is from the single station H, and then interpolated along the line. The arrows here are approximately, I think this is Darling Fault, this is the edge of the Kurgan tectonic zone to the west. This is the Yuan shear zone. So basically, you have the surface structure like this, and then in the crust itself, I guess you can actually see the moho truncation, like very weak moho to the basin side, and then some sort of truncation beneath the Kurgan tectonic zone. But here, I guess the Yuan shear zone, the moho here is relatively in smaller amplitude. And then the middle panel here shows the velocity in variations. So basically, I removed the mean of this just to show better the lateral changes in the velocities. Like here, this is the Perth Basin, and then there's some sort of fast mid to lower crust down there. And then east of the Darling Fold, I guess we've seen this in the early in this morning's presentations, but I need to point out actually MT also shows some sort of conductive feature right here. And then across these two different surface regions, I guess, well, the crust is not like a pure green or pure blue. It's different domains. So this is a southwest one line. And then this is Midwest 2 line like this, again, west and east. Just approximately, this is where the Darling Fault is. Perth Basin to the left, to the west. And then, again, this is the velocity gradient. So, velocity variations. So it's very different across the Darling Fault. One thing I need to point out is, okay, Darling Fault is here. You can actually see the slow velocities sort of migrates into east of the Darling Fault. This is actually true for this line and also previously here to the southwest one line as well. The next one is this Midwest 1 plus Huaiyu 3 line. So I guess, again, I put the Darling Fault here. You see the Perth Basin signal, slow basin signature, and then it migrates towards the east. That's one feature. And also in the middle of this part of the Yukon, you see a moho step. So this sort of spatially correlates with different velocity domains. So the Yukon, or at least the UME there, is not a uniform feature. This is from Erdinch's Amisaro group. Basically, they developed this so-called autocorrelation technique, which is sensitive to the velocity, shear wave velocities and P wave velocities. And by combining these two, you can have actually a 3D VPS ratio. So earlier I showed a crustal bulk crust or average crust to VPS ratio, which is just like average of the whole crust, but they can actually show a 3D VPS ratio. So basically, these are the VPS ratios along three active source lines. Again, I guess it's complicated. It's not a single cratonic look. Going forward, so I guess I'm just going to show this is combining phase 1, phase 2, and half of phase 3 data plus the permanent stations or the backbone stations this is the whole WA. And then the ray density there, the map there shows we can actually start forming whole state models. And then that's one thing. So starting from phase 3, we're going to produce whole WA models. And then also we're going to add more model to this. This is like the same two stages, Mikathera and NWAO, with the rest of, I think now is with all three phase stations. So for radio wave and lava wave, the idea here is we can form some sort of, this is a bit complicated, but I guess it's called radio anisotropy. And by using this, we can have a 3D model of the crust, which will show the fossil fabric in the crust, which will help us understand the early crust forming mechanisms. And then the next thing to do is very obvious. JP will show this. This is his model, but here I'm just stealing this to show, okay, we have the crustal shear wave velocity model like this, very busy. And then this is the surface wave, earthquake surface wave shear wave model. If I glue this together, you can actually see quite different resolution. So we can actually combining these two data sets and then invert structure all the way. This is going down to maybe 140-ish. And then we can have some sort of nice looking models. I think that's all I have.